Today we have the great pleasure to welcome Professor Ullrich Köthe. I'm not sure that my pronunciation is quite okay, but who is a professor in the visual lab in the University of Heidelberg, and who is the head of the Interpretable AI. I mean, trying to open the black box and see how we can better understand what's going on inside the black box, and how to use the neural nets to better understand typically what's going on in our say physics and other models. And today Ullrich will talk to us about invertible neural nets. So everyone is welcome. Please cut your mic while during the lecture, and at the end you can raise your hand, please, in the chats, and we'll have rounds of questions. Okay, so thank you, Ullrich, for being there. So the floor is yours, so to speak.
Yeah, thank you very much for this interesting invitation. So I will share my screen. So now you should see my slides.
Yes, we do.
Yeah, and I would like to start with thanking my amazing group. The name of the direct collaborators to today's results are listed here, but there are more interesting people. Okay, so this presentation comes from a tutorial that I held at ECCV back in August. So the material should be online somewhere, but I don't know whether it's freely accessible. Of course, it was an online conference, which took away much of the fun of a conference. But anyway. Okay, so let's start. As you see, I'm mainly interested in natural sciences and life sciences and social sciences, so applications of neural networks to these fields as a tool of understanding, as a tool of gaining insight into an application, into a scientific application. And one of the most important things in science is to characterize uncertainty. Yeah, and I will just give a short overview over sources of uncertainty in order to motivate why inverse problems, as we address with INNs, are so important. So let's say we have some unknown. Do you see my mouse, by the way?
Yes.
Okay. We have some unknown conditional probability P star of y. So let's say y are observable quantities and x are the hidden quantities that we are actually interested in. Yeah, and P star is the true relationship between the two. And what we like to know is a approximation Q star, which minimizes some loss function between Q and the true relationship P star. Yeah, and of course Q cannot be arbitrary but must be taken from some tractable model family. So, and first let's look at the error sources at in the deterministic case. So we say that y is a deterministic function G star of the axis, not a probability. And then we have first model specification error. So F does not contain a good model for G star. Yeah, and what we then get is a model F star that is as good as possible, but not the same as G star. This used to be a very big problem, but somewhat disappeared due to neural networks. So so neural networks are such a powerful model family that model misspecification is not our main concern anymore at the moment. So the second one is called the epistemic error. So we don't actually know G star, but we only have a finite training set. And since finite training sets can only have so much information about the truth, what we actually get is not F star, but F tilde, which differs from F star. So it's the best for the training set, but that may not be the best overall in terms of generalization error. So the third source of error is optimization error. In practice, we may not even be able to find the global optimum of F tilde, but we will actually find an F hat, which may differ according to the quality of our optimization algorithm from the best possible solution F tilde. So now, if we get back the probabilistic nature, so we now have not a deterministic but a probabilistic mapping from X to Y, we have two additional sources of uncertainty. First is the aleatory errors, so the X's themselves and the P star are noisy mechanisms, so don't give the same outcome every time. And one classical solution to this is to reduce it to the deterministic case by taking the expectation or taking the maximum a posteriori estimate. Then we get back a deterministic function. Another, and this gets us to the inverse problems, is the ambiguity error. So the X's may not fully determine the Y's. And so several Y's may be equally good solutions from a mathematical point of view. And then the classical solution is to add a regularization term to the loss, which disambiguates the solutions. But, of course, doing everything in a Bayesian manner is much better because you do not just reduce your problem to a deterministic problem, but you fully keep the probabilistic nature by determining a full posterior rather than a point estimate. But the problem is it's a lot more complicated. So we have a much bigger problem with model misspecification, or we have very powerful models that are expensive and hard to solve. And the interesting thing is that invertible neural networks offer a lot of new possibilities in this respect for Bayesian estimation. So let's see where the ambiguity comes from. So we have a so-called forward problem. So we have X's, and these X's are mapped to Y's, but the mapping is not unique. So several X's are mapped to the same Y. And the inverse problem is to go from the Y's back to the X's. But since it's ambiguous, it's not clear what we should do. So for example, for the lower Y, we decided to just pick one of the possible X's, a point estimate. And for the upper Y, we decided to take the average of the possible X's. And both it's far from ideal. The average may not even be a plausible solution at all. And if we just take one solution, then we lose the information that there are actually diverse solutions. So, and this happens quite often. So, for example, in crystallography, in environmental physics, in tomography, in biology, and so on. And I will later on show a few examples of problems that we solved using invertible neural networks. So here is a very simplified linear case. So let's say the X's are three-dimensional, all normally distributed, and the Y's are, so X2 is identical to Y2, but Y1 is the sum of two X's, so we lose information. And in matrix notation, this is a simple matrix multiplication, and the matrix A is of course not invertible, so we cannot just compute X equals to A inverse times Y. That does not work. And regularization is one possibility. So for example, you would take one solution that has the smallest norm in the null space of the matrix. Yeah, that would be a typical regularizer. But in the Bayesian approach, you would list all the possible solutions and give them a probability. Or you would create a sample from the solution space of the inverse problem, which is representative for all the possible solutions. Yeah, and our idea to achieve this Bayesian approach is to augment the Y space. So we have Y1 and Y2 as before, but now we have a new variable Z1, which is the difference between X1 and X3. And now the augmented A matrix here is invertible. Yeah, and then once we have the augmented Y space, we can just apply the augmented inverse and get back our X. Of course, the problem is now that we do not know Z1. First, we just introduced it. Yeah, but it's easy to calculate from the forward problem that Z1 must be normally distributed with a variance of 2. Yeah, because it's the difference of two normally distributed variables. So what we can do is we can sample Z1s from the appropriate distribution, insert these samples into the augmented Y vector, and then compute a sample from the inverse. Yeah, and then we can repeat this many times. So draw many samples of Z1, and then we get many samples of X. Yeah, that's our main idea to solve this inverse problem. And you can say it's equivalent to the reparameterization trick. Yeah, so we reparameterize the ambiguity by introducing this auxiliary random variable Z1. And this works if the Z1 variable is statistically independent from the Y variables. So otherwise we could not sample Z independently of Y, which we want. So now generalizing this, so we now do not have a linear relationship, but some arbitrary relationship S, and the inverse function S inverse is ill-posed, so we have it is one to many. Yeah, and we do the same thing. We introduce additional variables Z, and then find a augmented function S aug, which has two properties. First, the Y part is the same as the original S, and the Z part follows some known distribution so that we can easily sample later on. Yeah, typically normal distribution. And then the augmented S must be invertible, so it's constructed such that it is invertible. And then we can insert the actual observations Y and a sample from Z, and then we get a sample from X. Yeah, and as I said, the S augmented must be invertible, and we must still guarantee that Z is statistically independent of Y. So now, how does it look in a diagram? So on the left, we have the original one-to-many mapping that it's hard to solve. And on the right-hand side, we have this augmented mapping, which is bijective. So this is easy. And the interesting thing is that we can construct this augmented mapping using invertible neural networks. So invertible neural networks have three properties. Is there a question? No?
That's all right. I think that perhaps someone has their mic. Oh. Okay, so sorry, you can please go on.
Yeah, I just continue. So an invertible neural network can run forward and backwards in the same way, in contrast to a feed-forward network, which only works in one direction, right? And then a bonus is that many implementations of invertible neural networks have tractable Jacobian determinants. And this is very, very useful for the algorithmics later on. So back to the slide with the general inverse problem. So what do we do in order to solve this with invertible networks? So this augmented function S will be implemented as the mapping of the invertible neural network, which we here call f zeta of x. Yeah? So this is the forward mapping. And then we ensure that the y part of this augmented function coincides with the original s of x by having a loss on y. And we ensure that the z part follows a known distribution by having a loss on the z part. And then the two properties that we require for this to work, so that as org is invertible is automatic because we used an invertible network, and the independence between z and y is enforced by these losses. Yeah? So we choose them such that this independence will be enforced when the model is converged. So here is a bit more information about the losses. So actually we can also use 3 losses in addition a loss on x. So this is not really needed because upon convergence it will automatically be 0. But in practice it converges faster if we also have a loss on x. So let's see what we have. So Ly must ensure that the y part corresponds to the true observations in the training set. So we have just, for example, squared loss to ensure this. Yeah? So f zeta xi, y part is the forward transform of our network, and yi are the true observations. Then that z matches a standard normal distribution is ensured by what's called the MMD loss, which I will explain in a second. And that Lx matches the distribution of some prior on the axis is also ensured with an MMD loss on the inverse of the neural network. So running the network backward should give us the correct distribution of the axis. So what's MMD? It's the abbreviation of maximum mean discrepancy, and it's defined on 2 batches. So B coming from one distribution, for example, the true distribution, and B prime from another one, for example, the distribution represented by our network. And then it's a simple expectation over 3 kernel computations. Oh, here is a closing bracket missing. Yeah, and so we just compare all the samples through the kernel, and the most popular kernel is the inverse multi-quadratic kernel for this, because it also gives gradient if the 2 distributions are very far from each other. Yeah, whereas a Gaussian gradient only gives a Gaussian kernel would only give gradient for very similar samples. Okay, so and now once we have trained our network, we want to do inference. So going back from observations y to the underlying axis. And as in the linear case, we do the same thing. We have given y here, and then we sample az from the known distribution and compute the corresponding x by running the network backwards. And then we repeat this with many different z's and get a sample from the desired distribution x. Or for a given x, we can also use the change of variables formula that's not shown here in order to compute the probability of this x. Yeah, and there is a simple theorem. When the losses are actually equal to 0, then the sample that we create will actually follow the true distribution that we would like to model. So we don't yet have asymptotic results, so how big the difference is when the losses are still small but non-zero. This is an interesting theoretical problem that needs to be solved. So now you may wonder, how can you make a neural network invertible? And the interesting thing is that you can construct invertible networks by using non-invertible parts. So, and combining these parts in a clever way. And the network that we prefer is called the real NVP, non-volume preserving network. And this consists of a sequence of coupling layers. So this shows a coupling layer, and I will show in a minute how it works. And then the input of the coupling layer, X, is split into two subvectors of half the size. So if X is 10-dimensional, X1 and X2 are 5-dimensional subvectors. And then we use the second half to compute coefficients for a affine transformation of the first part, and then we use the first part to compute coefficients of an affine transformation of the second part. Yeah, and these subnetworks to compute the coefficients are just normal feed-forward networks or convolutional networks, depending on the application. Yeah, so these are non-invertible, but you will see in a second. So this is the affine transformation that the network implements, and you see that it's easy to invert because you just have to solve the linear system for the input variables. Yeah? And that's what is shown here in the second line. So here's an animation of the whole thing. So this is the coupling layer again. So we have an input and split it into two halves. Then we compute purple coefficients from the lower part. And then we use the purple coefficients to compute red results for the upper part. And we also use the red results to compute orange coefficients. And we use the orange coefficients to transform the lower part. And then we combine the two parts in order to get the output. Yeah, and then running this backwards just inverts all the arrows except for the ones in the middle. So we have the upper part, the red result, and we can compute the orange coefficients and then use the inverse transform to get back the green input for the lower part. And then we can use the green lower part to compute the purple coefficients and apply the inverse computation to the upper part. And then we can combine the two results and get back our input. Yeah? That's how this real NVP architecture works. And the important thing is that the inner networks are in both cases run only in the same direction, in the forward direction. So they don't have to be invertible. Yeah, actually, we found, and others as well, that a simpler version of this works better in practice. We only transform the upper part. So it's the first half of the previous diagram. Yeah, and the lower part is just a skip connection. And then when we stack many of these, we have orthogonal matrices in between, which mix the dimensions of our problem in typically a random way, yeah, before applying the next transformation. So what goes into the skip part changes according to these orthogonal matrices in between. So, and this means that if the chain is long enough, that everything will be mixed with everything at one point. So we can express really powerful transformations using this way. So there was even a paper that claimed that it is a universal approximator, but we are still trying to check the proof. So we are not entirely convinced whether the proof contains a gap. So now a toy application, inverse kinematics. So we imagine you have a robot arm with 4 degrees of freedom. So the first degree of freedom is the position of the arm here. So it can move upwards or downwards. Yeah, it is a 2-dimensional arm. can move upwards or downwards, and then the other three are angles of the joints. Yeah, so the arm can move up and down. Can you see me? And then change the angles. Yeah, and then there are prior distributions on these 4 degrees of freedom, which mean that the arm in its natural position will prefer to be in the area here between the 2 lines. Yeah? So, and then we have a hand position, Y. This is the output of the forward model. And since the hand position is 2-dimensional, whereas the arm is 4-dimensional, we lose information about the positions of the arm and the joints. And this is our forward function s of x, and we augmented it with 2 additional dimensions, which are supposed to capture the information that is lost in going forward to y. And then the inverse problem is we fix some hand position where we would like the arm to land, and then we would like to know all the possible values of x along with their probabilities, which adjust the arm so that it ends here in that point. Yeah, this is the inverse problem. And this is interesting because it is clearly bimodal. So you can either reach through the top or through the bottom, but if you reach through the center, the arm will be too long and not reach the desired position. Yeah, and many solutions such as regularization would only find either possibility and not both. And that's why this problem is interesting. So here is 2 results. So ABC is a sampling method, very, very expensive. So rejection sampling for ground truth. And invertible neural networks gives a distribution that looks reasonably close to that. Yeah, and here this region is the positioning error. So if we take one solution of our network and then adjust the arm according to that solution, it will not always exactly reach the desired position, but it will always be close. Yeah, and then down here are some simpler positions where there is only a unimodal solution space. Wrong way. And then we compared this with a lot of other network types, invertible network types, which I don't have the time to talk about in detail today. And it turns out that the invertible networks give the best results. So here you see a diagram. So we measured the purple results are how close the distribution of our network is through the ground truth distribution of ABC, and the red one is how large the positioning error is if we use our parameters. So, and you see that we win here. The last one is also very good, but not invertible. And then here are autoencoders, which are also quite good, but have a larger spread of the result. And here, for example, inverse autoregressive flows and iris nets are a lot worse. But this has to be taken with a grain of salt because the iris net in particular has been improved a lot in the last year, and we haven't included these results here. So here's the first real application. So here we have multispectral endoscopy. So you have a minimally invasive surgery. And so you look into the body through a camera and also insert the surgical instruments through some very tiny holes. And then a very important problem for the surgeon is whether the blood vessels have been clipped appropriately before the surgery starts. Otherwise, you will get a big mess if you cut into an active blood vessel. Yeah, and you cannot see this easily from RGB images, but we found that using multispectral images, you can see this. Here are clips And then you see here, blue means that the blood flow has been stopped, as measured by blood oxygenation. So here the surgeon can be safely start cutting. So, and then the task is, of course, we have the spectrum of our camera, and we would like to know certain tissue parameters like blood oxygenation. And this is clearly an inverse problem, and our collaborators have implemented the forward problem by Monte Carlo simulation, as you see here. So there are some tissue parameters, and then they performed a very expensive ray tracing routine. So they had light particles being scattered and eventually reaching the camera, and then you can see the spectrum that reaches the camera when you know the spectrum of the original light, and then the spectrum is discretized according to the properties of the camera, and that's the observation that follows from a certain setting of the input parameters. And now we train our neural networks using the simulated data, as I explained earlier, and then we can later on invert it. So we insert the actual spectrum that our camera observed and also random numbers for the unobserved stuff, and then we get back our axis by running the network backwards. And here are the findings. So the top row is the expensive rejection sampling that we run for ground truths. The second row is our network, and the third and fourth rows are alternative networks that have been proposed. So the conditional, variational autoencoder, and dropout Bayesian inference. And you see a number of interesting properties. So here, for example, our network is able to find a skewed distribution. Yeah, the volume fraction cannot be more than 100% or so. And then the distribution should not exceed the physical possible stuff as it does down here, yeah, in the other methods. And then our method also finds that tissue thickness and tissue anisotropy are essentially unrecoverable, unidentifiable. So the posterior distributions are equal to the prior distributions. So we have not learned anything about these. Whereas the other methods still have a nicely peaked Gaussian distribution, so they pretend to have found something there. Yeah, and the reason why this is possible with invertible networks is because there are no a priori restrictions on how the shape of the distribution may look like. So we can represent any arbitrary distribution using the network. And also the same findings here with the correlation between certain parameters. And if you compare with the other methods, they have symmetric distributions where they should be skewed. They have overconfidence when the parameter is actually unrecoverable, and they have too much or too little correlation between the parameters. Yeah, this was the first success in practice of our neural network research. And then another application of this is which camera you should use. So there is the possibility to use a standard RGB camera, or to use 8 spectral channel or 27. And of course, the more channels you need, the more expensive the equipment will be. And so you would like to avoid the 27 spectral channels. And then we compared the posteriors for blood oxygenation here. So, and the first one is multimodal. So you have 2 maxima in the posterior. And the ground truth maximum is the one with lower mass. So the network would return the wrong value, and that's not what you want. The second one, you have a very high variance. So the ground truth is still within the, let's say, 2 sigma region, but that's not good enough. And the third one is what you would like to have. Nicely unimodal, narrow posterior. And that's actually the posterior of the 8 spectral channel camera, whereas the first 2 come from the 3 spectral camera. And the conclusion is that the 8 channel camera is sufficient, whereas a normal RGB camera is too weak. So this is an example of how you can do experimental design using invertible neural networks. So I have shown one variant of the invertible neural network where we split the latent space into the Y and the Z part. That's what we call the augmented latent space. But there are two more possibilities. One is called the latent mixture INN. So we only have Z in the latent space, but Z is not a standard normal distribution, but a mixture of Gaussian. And we have one mixture component for every Y. So, and this is particularly useful is Y are discrete labels. For example, the MNIST digits. Yeah. So then we have a Gaussian function in latent space for every digit. So 10 Gaussian functions in latent space. And unfortunately, I don't have time to go into details about this interesting architecture. And then there's a third one, which we call the conditional INN, where we also still have a latent space that only contains Z, so the random numbers, and Y is a side input to the neural network. So instead of having the neural network a function of X, it's now a function of X and Y. And this function is constructed such that it is invertible in X. It doesn't have to be invertible in Y. And yeah, that's what I just said. So the dimensions of X and Z must be matched. And this turns out to be very useful because we don't have to decide how many dimensions Z you need. And you can also train with maximum likelihood instead of MMD, which turns out to be to give better convergence. So let's see how this looks like. So we have already seen this coupling layer. And now the internal networks S and T just get an additional input. Yeah, that's it, essentially. Yeah, and since these are just feed-forward networks or convolutional networks, adding more inputs is very easy. Yeah, and then the mapping is a function of X to Z, but it's also a function of Y. Or you can also say for every Y, the network selects a different mapping from X to Z. Yeah, and when we stack many of these layers. So what we often do is that we pre-process Y by a conditioning network. So that is essentially a feature detector. Yeah, and this is especially important when Y is a complex information, such as an image. You will see examples in a minute. Yeah, and then the output of the conditional network is fed to the individual layers. Yeah, and so now it doesn't compute a function of Y directly, but a function of phi of Y, the invertible network. So here this is phi is green and F is orange. So now I present the change of variables formula here. So the mapping, the conditional probability of X given Y can now be expressed by the probability of the Z that we get if we run our network in forward direction times a correction, which is the magnitude of the Jacobian determinant. Yeah, and so this correction adjusts for the local volume change of the network. And when we insert this into the formula for the maximum likelihood loss, which is this one, then it turns out that the network architecture gives us a very simple formula for the maximum likelihood loss. So it contains of two parts. The first one is here. So this is actually the logarithm now. Yeah, the logarithm of the likelihood. And the logarithm of a normal distribution is just the squared loss here. And the logarithm of the Jacobian determinant is just the sum of the outputs of the S networks. Yeah, and this is a trick. So the network is constructed such that all the Jacobians of every layer are triangular matrices. And so the determinant is just the product of the diagonal elements, and the logarithm is the sum of the logarithms. So, and that's essentially what this formula says. Yeah, and then to run it backward, we do what we have always done. We sample a Z and then insert Z into the network and the actual observations Y as well, and run it backwards and get the sample from X. So here's the same as an illustration. So the forward is the training path. So we have ground truth pairs X and Y, and we run the network forward, and we ensure that Z is normally distributed, so that the network is trained such that Z becomes normally distributed, given ground truth pairs X and Y. And in the inference phase, we sample from the normal distribution, insert our observations Y, run the network backwards, and get a sample from the posterior distribution. So here is how this can be applied to images. There, the right-hand side is the invertible network, and the left-hand side is the conditioning network. So the condition here is an image, in this case a Google Maps image, and this is pre-processed. So we compute features of the map at different scales, and then insert it to the invertible network, and then taking a random vector Z, running the network backwards, we will get a satellite image that corresponds to the map image that we inserted. Yeah, so it's similar to the cycle guns, but it uses a different principle. And here are some results, in this case for day to night conversion. So on the left-hand side is the day image. On the right-hand side is the ground truth night image taken from the same position. And in the middle are outputs of our networks, which all look like plausible night images of the given scene, but they are diverse. And that's the great thing about Bayesian inference. So you get diverse solutions, and all these solutions are equally plausible if you don't have additional information, right? And here's what the conditioning network does, the feature extraction network for this particular sample. So we have at a very fine level, the conditioning network, the pre-processing feature detection network, computes edges and textures. On the second level, it differentiates between foreground and background. So in this case, sky and the city and the wood. And level 3 identifies cities because it needs to switch on the light there at night. Yeah. So you see here in these results, in the forest and in the background, there are no lights, only the city has lights. So, and another application, now coming to science, is simulation-based inference. So in that case, we assume that we have a simulation program for the forward process already, yeah? And this is often the case. So if you have a differential equation or a Markov chain or a Monte Carlo simulation, then you have already a model for the forward process. But the task in many applications is not to run the forward process, but to invert it. So given observations, run the simulation backwards, and that is not so easy. And so what we do is we apply the Bayesian formula. So in principle, the inversion is straightforward. Just insert everything into the Bayesian formula. But the problem is that this forward likelihood, P of x given theta, so the parameter, is usually at least untractable or often only implicitly defined. So the simulation gives you samples, but not numerical values for the likelihood. Yeah, and then this is called likelihood-free inference in the literature. And what we do is we solve Bayesian's formula, Bayes formula with invertible neural networks. So here is what we do. No, this is not what we do. That is the expensive traditional solution. So rejection sampling. So you repeat very often. So it's very expensive. You sample candidate parameters, then you run the simulation, and then you look if your simulation results match the observations reasonably well, so as defined by some distance measure. And if the simulation matches, then you keep the parameters where the simulation started with, and otherwise you reject these parameters. And then if you repeat this often enough, you get a reasonable sample of parameters that could explain the observations. And as you will notice in COVID research, this is quite common to do this, right? So they have the epidemiological differential equations that I will show in a minute. And then they tweak the parameters until the simulation outcomes match the observed data. And that's essentially a handcrafted version of this. There are other possibilities that I will not go into detail right now. And what we do is we use the simulation to train an invertible neural network. Yeah, so here is the approach that we call Bayes flow. So here in the gray box is the training. So we sample theta, run the simulation, and then use the theta and the outcome of the simulation as a training example for our invertible neural network. Yeah, and then we repeat this many times until the neural network becomes an expert for this type of application. Yeah, it's similar to pilot training. So imagine you have a flight simulator that is so realistic that a pilot can just train on a flight simulator, and then once he is an expert, you put him in a true plane, which is our truly observed data, and then feed it to our INN, and then it works. Yeah, that's simulation-based training. So here is a bit more complicated version, or also better version. So we have actually 3 networks. No, here we have 2 networks. So we have a summary network that's the same as the feature selection network from the day-night application. And then we have the invertible network that is doing the actual inference. So this is a conditional INN. So let me show some applications of this. Here it shows just, and I will skip that more or less, that it works on toy problems. We don't have the time to go into details here. So I would like to show the COVID application. So here the forward model is what's called the set-seared model. So we have susceptible, that is are the people who could potentially get ill. Then the exposed, and that's the people who have been infected but are still appear healthy. So they are not themselves infectious, cannot spread the disease. And then we have the carrier, which are ill and can spread the disease, but they don't know about this. Yeah. So that are, for example, the asymptomatic cases. And then the infected are the ones that know they are ill, so have a positive test or are in hospital or whatever. And then we assume that if you die from the disease, you have manifest symptoms before, so you are in the infected compartment. But if you have no manifest symptoms or very weak symptoms, you can recover without ever being detected. Yeah, and the recovered people are hopefully immune, at least for a while. Yeah, so they are not again susceptible. You could also insert a loop from here to there, which measures how long people will remain immune. So they are the healthy, they may get infected, they are symptom-free and cannot spread, they are symptom-free and can spread, they are ill and can spread, they are healed and they are dead. And here are some of the parameters. So gamma is the rate from getting infectious. So 1 over gamma is the incubation period. Then here is the rate of moving from the carrier to the infected and on to the recovered compartment. And the sum of the reciprocals is the time you are infectious, yeah, on average. And then here are two parameters. Alpha is the fraction of people remaining undetected, also they may spread the disease. And theta is the rate of getting healed. So 1 over theta is the infectious period of the asymptotic cases. And lambda is the infection rate, and that's the quantity that we try to reduce by lockdowns and things like that, right? That's why it's a function of t, of time. Yeah, and in differential equations, it looks like this. So here are the parameters I just explained, and the derivatives just depend in a nonlinear way on the previous numbers. So, and then to enhance realism, we also need a observation model. And this models 3 recording errors. One is delay. So until someone is registered in the system, it takes a week in Germany or so. Then we have noise, because of course that's very noisy. And we have a weekly modulation, because on weekend people are tested a lot less than in the week. So, and you have to take this into account. And then we need an intervention model, so some idea how the infection rate changes over time. So, and here we modeled it as a piecewise linear function with certain change points. But you should remember, we have priors for these change points, which are the dates when these measures took effect. But of course, so they're officially introduced, but that doesn't mean that everyone conforms to the requirements, right? And so the actual effect will be learned. So we only have a prior, which is the hoped for effect, but the actual effect will be learned by our INN. In total, we have 34 parameters, and we have 3 time series of 60 or 80 days, depending on how long we train. So we have, for example, around 200 input parameters and 34 output parameters. Yeah, and here's the network. So in this case, it consists of 3 parts. We have a convolutional network, which just filters the time series. So it does feature detection and noise reduction and so on. Then we have an LSTM, which reduces variable length time series to fixed length statistics. Yeah, because our invertible network can only process fixed size inputs. And then we feed these statistics to the invertible network, to a conditional invertible network. So the statistics are the conditions. Yeah, and then we train this end-to-end by running the simulations very often. And then to get results on real data, we run the network backwards. And these are, for example, the posteriors of the 34 parameters for Germany. And I would like to emphasize this one. This is the alpha, is the probability of remaining undetected. And we have an uninformative prior, a uniform between 0 and 1. But the outcome is very, very far from uniform. And the peak here is at 83%. So 83% of the infected people remain undetected. And this is very much in line with the zero prevalence studies that have been published recently. So they also find that only about a sixth of the population has manifest symptoms or tests so that you can detect them. So here are the resimulations. So when we start from our posteriors and run the simulation again, and then we get the median simulation, which is the dark line. And this is almost identical to the observations. So here, in the cases of that, there are some small deviations. And then we also get confidence intervals. So the 50, 90, and 90%, 95% confidence interval. That's the big advantage of doing a Bayesian approach, that you get these confidence intervals. So, and we know, for example, here, if you see the cumulative effect infected, it's very unlikely to be less than 100,000 when the reported number was 200,000. Yeah. So, and this is the daily. This is the cumulated. The daily is just with the weekly modulation, more or less. Yeah, you nicely see the drop at weekends. And here are the calibration results. So that means calibration in this context means that we measure how well the uncertainty estimate of the network agrees with the true uncertainty. Yeah, when the network thinks it is 80% correct, then it should be correct in 80% of the cases and not in 90% of the cases, in which case the network would be underconfident, or if it were actually correct in only 50% of the cases, it would be overconfident if it claimed 80%. And the calibration curves should just be flat histograms, and most of them are actually flat histograms. Only the last two here have a slight drop in the middle. Yeah, but I forgot the explanation for that. Yeah, so I think time is up, so I cannot show the remaining applications. But I have lots of backup slides, so if you have any questions, I can show them. Thank you very much.
Thank you. Thanks a lot, Ullrich. So I'm sorry that we don't have a general sign to say hello with everyone, right? Thank you for this very inspiring talk. And this opens plenty of questions. So I will see whether, I see that, okay, so many people are saying thank you. And then the question is there someone raising their hands? Oh, perhaps Bertrand. Bertrand, do you want to say something? I don't know actually whether everyone can speak.
No, I was just saying thanks a lot for the great talk.
Yeah.
I could attend, not fully, but the part I saw was really, really great. Thank you. I will really read in detail your publications. I'm very curious about all these results.
Yeah, thank you. Curious. I think that I saw a question from our friend Zabo. Where are you?
Hello.
Yes, please. So you have a question, right? Yeah,
Yeah,
well done.
exactly. So I was wondering at the beginning of your talk, when you defined these objective functions, there were three different terms like L1, L2, L3.
Yeah.
Could we go back to this part?
Mm-hmm. Might take a while because there are so many slides.
And if I understood correctly, basically you use these MMD to measure the difference between two distributions, out of which you had samples.
Yes, I had a question on this too. Right.
So what I was wondering is, I guess,
No, I have it. So here.
yeah, exactly. So this part, the basically LZ and LX. So I assume that some of the distributions here, like let's say PZ, is something which is given. Is it correct?
Yeah, P of Z is a distribution that
Oh, sorry, P star X, these, which shows up in LX, the second argument.
The second line, yeah? LZ, you mean?
No, in LX, the loss function LX, there's this P star X.
Mm-hmm.
So that's something given. Is it correct?
Yeah, P star of X is of course unknown, but we know a sample of it, and which is just a set of training data. Yeah.
Okay. And how about the other one, is PY, PZ?
PY. PY is the distribution of the observations for the training data.
Yep.
And PZ is a distribution that the network designer must define. Yeah, so PZ can be any arbitrary distribution.
Yep.
And I, as the network designer, choose a distribution that's easy. And the typical distribution is the normal distribution. That's why this entire approach is also called normalizing flow. Because you can interpret the network as a flow from the X space to the Z space. And when the Z distribution is normal, then it's a normalizing flow.
So this PY times PZ is something known. Is it correct?
Yes.
Okay. So what I was wondering is, in this case, so there are also divergence measures, like let's say variants of MMD called Kernel-Stein discrepancy, where one doesn't need samples from the distribution itself. It is sufficient to know it up to normalizing constant.
Yeah.
So what I would expect intuitively is that probably these kind of divergence measures can be more sample efficient.
Yeah, that's possible. But on the other hand, for most of the application, in the meantime, we switched to maximum likelihood training and do not use MMD at all.
Okay. Bad luck.
Yeah. Well, actually, I had a question.
Right.
Yeah, go on. Sorry.
You are right. So one very interesting idea is to combine an invertible network with what's called an energy network, which provides an unnormalized probability distribution.
Yep.
Yeah, and we think that by combining these two, we can represent more complicated distributions better. So we think that the expressive power of the networks will be better utilized by this combination. And then we need a loss that can train the energy network. And then the things that you mentioned will become important.
I see. Okay, then there's one more comment, because these ones also have some linear time variance. So if sample size is an issue, like bottleneck, then there are also fast versions of these. These are just 2 quick comments.
Yeah, so of course, sample size is a problem, but since we often use simulation-based training, so it's just a matter of computational resources. Yeah, so we just need a bigger cluster to run the simulations in order to create enough training data. And so it doesn't waste our researcher time, it just wastes compute.
The PC.
Yes.
I see. Okay. Thank you very much.
Thanks a lot. So if you can see the comments in the chat, so everyone is just thanking you. So I will start. We have 2 questions. So everyone, if you want to put your questions in the chat, that's great. Augrisel, okay, I don't know who you are, but I will start with the 2 former questions. One is, okay, I'll start with a simple one. Xur is saying, why do you need a multiplication in the invertible neural net architecture since nonlinearity is handled by the internal networks? And the next question will be by François L. Land, perhaps.
Yeah, so the answer is the nonlinearity only is used in order to compute the coefficients of the transformation. But the transformation itself is so far linear or affine. Yeah, we have an affine transformation whose coefficients are computed in a linear way, in a nonlinear way. And you can also drop the multiplication. In that case, the network is called a nice network. And then one effect is that the Jacobian is automatically, the determinant is automatically always 1. So you can drop this term from the change of variables formula, and then it's a volume preserving flow. And obviously a volume preserving flow is not as powerful as a non-volume preserving flow.
Mm-hmm.
Yeah, and then the affine layers are still pretty weak, but we find that by stacking many of them, we can still implement very complicated transformations, and it's not clear why a combination of so simple transformations results in very complicated transformations. So that's something we are currently investigating. But you can also solve the problem the other way around by choosing a more complicated transformation. So instead of affine, you can choose higher order polynomials. So one popular choice are the sum of squares polynomials, because they are guaranteed to be invertible.
Mm-hmm.
Yeah, and then you can have nonlinear transformations as well. And still, it's only the coefficients that are learned by the internal networks, not the transformation itself.
Okay, I see the point. Sur this, okay, it says okay. So we have another question. The second question was by François Land. Can you hear me, François? Are you still here? Okay, so
hello, thank you.
Yeah. Here you are.
Yes,
good.
you hear me. Maybe it's a silly question. So in this slide that now is a big gray box for me, if does it make sense to want to maybe relax the constraint that you want Y and Z to be independent, in the sense that if you imagine that you have a problem where you have partial observations and there is a latent variable, but okay, maybe some piece of it is independent from the observations, and maybe some piece of it is a truly dependent latent variable that you cannot observe directly, but exists and is correlated with the true values of things. Then could you change the way you learn such that you would sort of discover this meaningful Z variable?
Yeah, so
or maybe it doesn't make sense. I don't know.
In principle, this is possible. So if Y and Z are dependent on each other, then we need to model P of Z given Y. Yeah, we cannot just use P of Z. And if we can learn P of Z given Y, and if it is such that we can sample from P of Z given Y, then that would be usable just as well. Yeah, and actually the variant that I just briefly mentioned, the latent mixture INN, is of that type. So we have the distribution of Z given Y is a mixture distribution where each label Y defines one mixture component. Yeah, and this is still, of course, relatively easy because it's easy to learn a mixture distribution and it's easy to sample from a mixture distribution. But in principle, the relationship could be arbitrarily complex, provided that it remains tractable.
Thank you.
Thank you. The next question is by Augustin. Sorry for your name. You raised your hand.
Yes. So, hi. Thank you very much for the presentation. I have a clarification. When you presented the slide on the conditional invertible neural network, you said that you sample from Z for a given fixed Y, and then you get a sample of X, but don't you get an expression of the likelihood of the conditional distribution of P of X given Z and Y? Do you get the ability to compute the likelihood or just a sample of X?
Yeah, so here is the slide, right? No?
I think it was the one with the architecture, but
yeah.
the diagram, but
here, then the lower formula is the one.
Okay, so here they have the full formula. Okay.
Yeah, so we get a sample from X given Y. Yeah.
So
when
you run the...
Do you know the reparameterization trick?
Yes.
So there the idea is to have a sample from a normal distribution given the mean and variance, right?
Mm-hmm.
Then they turn this into a so this is a probability, and then they turn this into a deterministic formula from mean and variance and a standard normal distributed random variable.
Mm-hmm.
Yeah. So and the important effect of this reparameterization trick is that the sampling distribution for Z does no longer depend on the parameters of the desired distribution of the X distribution. And that means that when you compute gradient, the gradients do not affect the sampling distribution. And we do the same thing, just for the conditional distribution of P of X given Y.
Okay.
So we reparameterize this in the deterministic function F inverse of Z and Y. And we train this inverse function, this deterministic function, such that we can just sample Z from a fixed distribution, a normal in this case. Yeah, so it's exactly the same trick.
Okay, thank you. I think I get it now. Okay, thanks.
Thank you.
Or you can just look up the reparameterization.
Yeah. So I guess that perhaps this answers also Cyril's question, who was asking how to you choose Z independent of Y. Okay, because you just sample Z from your prior distribution, right? So it doesn't depend on Y. Is it your question, Cyril?
Yeah, I see the question, so I can try to understand it.
Okay. Cyril says yes. So the next question we have...
Oh, I would like to answer it first.
Yeah, go
on. This is done by the MMD loss in that case. So the true distribution where the samples from the network are matched against is defined such that it is a product of a distribution on Y and a distribution on Z. Yeah, and when the network distribution converges towards this distribution, it's automatically also a product and therefore independent.
Yeah, thank you. So I don't dare. Actually, I could start. I could also put my questions in the in the chat, right? Because I didn't have time. I was wondering how you choose the dimension of Z. How many dimensional you need Z to be, or is it by trials and error?
No, the nice thing is that there is no freedom at all. So especially in the conditional INN and in the latent mixture INN, Z has always exactly the same dimension as X.
Okay.
So, and that's of course required for the transformation to be bijective, right?
Okay, thank you.
Maybe a follow-up question that you might ask later is, so how does it relate to variational autoencoders? Yeah, and these autoencoders always have fewer latent dimensions than X. So they have a bottleneck, and this is important for them to work. And we can also enforce a bottleneck without giving up the matched dimensions. And the trick is to split the Z space into important dimensions and unimportant dimensions. Yeah, and then the bottleneck dimensions will just be the important ones, and everything else will be put into the unimportant dimensions.
Okay. Thanks a lot. Would you like to take the next question following Cyril? So this is the Louis. Considering other distributions instead of just the Gaussian one. So perhaps Louis, if you are here. Okay, it was asking whether it would be easier to match the say to fit the X posterior if you have the freedom to choose as other distribution from your Z.
Yeah, so this is a very interesting topic which is currently under investigation. So the normal distribution is just the obvious choice. Yeah, and of course it has a number of nice properties. So one of them is that the individual dimensions are independent if you have a standard normal distribution. So it's just a product of one-dimensional Gaussians, which means that the latent dimensions are automatically disentangled. And one line of our research investigates whether we can guarantee that this disentanglement also makes sense from the application standpoint, so that we get latent dimensions that are interpretable. Yeah, and of course to do that we need a distribution that factorizes in Z space. That said, other distributions are possible and may make sense. So I have already talked about the mixture distribution, which is a good choice in some cases, and it makes possible to formulate a theorem about the disentanglement. Yeah, so we have a paper about guaranteed disentanglement, and that's the one with first author Peter Sørensen. And this theorem does not work if the latent distribution is normal. It needs to be a mixture distribution for the theorem to work. Another case is the tails of the distribution. So very recently, a paper was published that proves that the fundamental tail behavior, whether the distribution is short-tailed or long-tailed or medium-tailed, cannot be changed by a finite affine coupling network. Yeah, so it's just not strong enough. So if you know that your data distribution is long-tailed, you need a long-tailed latent distribution, for example, a student T distribution. Yeah. And I also already mentioned that we also consider combining the latent distribution with an energy network, so where it can be arbitrary, complicated. So, but these are all open questions.
Thank you very much. If you have another one, so there was a question by Miguel, okay, well, which was about the complexity of training an inverse neural nets.
Yeah, so this is essentially comparable to normal neural networks.
Okay.
So, for example, now we have a latent mixture INN for the ImageNet dataset. Yeah, and so with 1 million training examples or so, and training takes a few days or a week or so, just like a ResNet, more or less.
Okay, and then I will give me the floor as well. I was wondering whether, okay, so you said actually that MMD, you replaced it with the maximum likelihood. I was wondering whether at this point it would make sense to replace this with an adversarial network. Say that you see that when you invert, you generate your pseudo X with by sampling the Z, and then you would like to have this new distribution not to be different from the. So, did you consider?
That's also possible.
It's possible.
Yeah. We haven't had much experience with it yet, because we focused on making the maximum likelihood training better, and it turned out to be quite good already.
Yeah.
So, but we have this on our agenda to combine it with adversarial training as well. Oh,
great. I can see okay, so let's say that we still take 1 or 2 questions. So the next question by Alessandro is about the energy based. Is it RBM? So perhaps Alessandro, you might want to ask your question.
Maybe you meant Giancarlo?
Sorry, Giancarlo.
Hello. Yeah, so at a certain point, when we were talking about MMD and possible extensions, you mentioned that you are working maybe already on some ideas to use invertible networks together with some energy model. I didn't really understood what you meant by that. And so my question was is it like energy-based model like restricted Boltzmann machines or energy-based models in general? And what would be the idea? What would be the advantage if that's the case?
Yeah, actually so RBMs would be one possible energy model that one could use. And one could, for example, use the energy model to learn the latent distribution, so that it's not fixed to a simple Gaussian, or to correct the data distribution that the invertible network represents. Yeah, so let's say the invertible network only manages to do a good approximation of the data distribution, and then you could have sort of post-processing using an energy-based model.
Okay,
yeah, and
I see. Is that also
which they do it differently. I forgot the name. Stochastic normalizing flow, and there they alternate in the network between coupling layers and energy layers.
Okay, that's interesting.
That's also a very interesting idea in that direction.
Okay, I see. So okay, then thank you very much also for the talk and for your answer.
So thank you, Giancarlo. So I suggest that we have just the last question from Augrisel. Okay, Augrisel, would you like to?
Yes. Hi again. On the hyperspectral endoscopy experiment, you compared the approach with the invertible neural network with the ground truth that was computed with ABC, if I remember correctly. And how expensive was the ABC solution to compute compared to the INN solution? Remember, you mentioned that it was not tractable for non-type experiment, and this one looks like complicated experiment. So I was wondering about the computational complexity.
For example, in this example, you saw that for the unidentifiable parameters, the ABC posterior was still pretty far from uniform.
Okay.
The reason was that we could just not collect enough samples to get a good uniform distribution for the ABC approach.
Okay.
So, and the reason is to get good results in ABC, you must have a very big rejection rate. And so you waste most of your computation.
Okay. Well, maybe I'll need to check the slides again because I didn't understand it this way. Okay, thank you very much.
Yeah, so you have this distance between the true observations and the simulation outcome.
Okay.
And you have a threshold on this distance, and the smaller the threshold, the more accurate your approximation is.
Yes.
But the higher your rejection rate.
Yeah, and you're wasteful. Okay.
And you are extremely wasteful.
Okay.
So, and there's another question by you. Is it a problem for Z to be unimodal?
Yes.
This is a problem if the network is volume preserving. So if it has a Jacobian determinant of 1 everywhere, then we proved that the number of modes in the data distribution is preserved in the latent space. Or the other way around, if we force the latent space to be a unimodal distribution, the data distribution will also be unimodal. Yeah.
Okay.
Or if we use a mixture distribution in latent space, we will have as many modes as the mixture has, right? And
okay.
Surprisingly, in case of MNIST, this works quite well. So it seems that the data distribution for each MNIST digit is actually close to unimodal.
Okay.
But probably it will not scale to other problems.
Yes, because in the toy examples of the toy example of the robot, okay, still you have yes, you had a Z which was unimodal, right?
Yes.
And still the say the distributions you could either go by up or by the lower arm. So
yeah, but this was a non-volume preserving network.
Okay. I still have well, just one very last question. So can you learn something?
I'm not in a hurry. I can answer questions.
You know, well, say that at some point we'll stop and we won't keep you for the end of the night. Okay. It was anyway. There are so many questions and follow up. I think this is brilliant. I was wondering whether you could learn something by the difference on the X that you would generate depending on whether you would have a Z with high probability or low probability. Would that give something? Would that give an information about the say the landscape of the X?
Yeah. So one application that we explore, and it's also mentioned in the INN information bottleneck INN paper, is outlier detection. So some unpublished finding. So we can compute or maybe you know the typicality test that was published by Nalisnik. So outliers are samples that are not typical, so that fail the typicality test. And then we can apply the typicality test for ImageNet in data space using the change of variables formula. Mm-hmm. And then we find that the atypical images are those that have more texture or less texture than the average image.
Mm-hmm.
So these are the outliers according to this. If we apply the typicality test in Z-space, then we find that the outliers are images that are very busy, so that contain a lot of objects, like a bazaar photo in Asia. So, and then the third possibility, if we restrict the typicality test to the space spanned by the class centers, so we have 1,000 classes and 1,000-dimensional subspace, then the atypical pictures are the ones that contain several copies of the main object.
Okay.
So like not just one clock, but 15 clocks.
Okay, and just one, not one sheep, but several sheeps as well? Because having several clocks is a bit untypical, but having several sheeps might be more regular? Okay.
Yeah, I don't know. So that's, as I said, that's unpublished results, and we are still investigating what happens. So I can't. But I found it's interesting that depending on which subspace you use, you get different outliers, but all of them are plausible.
Yes. That's very interesting, the difference between this. Well, Ullrich, I just hope that we did not abuse your patience, because your talk was very inspiring, as everyone said. And thanks a lot. I just can't wait for this. Say that we can travel and see you face to face and have a beer together, all together.
Yeah.
Okay.
Okay. Back to Paris. It's about time, right?
Yes. Let's hope that this will come well, as soon as possible.
Yeah, but we will keep connected in online meetings.
Yes. Anyway, about Sam, whenever you want. Okay. This.
Exactly. So
as
soon as the student starts, he will probably ask questions.
Yeah. Great. Okay. Excellent. So thanks a lot. Thanks a lot to Ullrich. Thanks to all people. I can see that there are still 30 people online up to now. So it was a great seminar. Thanks a lot again.
Yeah. Thanks everybody. Goodbye.
Goodbye.